the implications of Newton's law. So the first one which we want to cover, it will be the Newton's third law. You all are familiar with it from the high school, action and reaction, right? So we have been potentially talking about that so far, but we didn't specifically mention that. For example, we brought the discussion of putting something on top of the table. So the thing what you put on top of the table, it has its mass, okay? Whatever it mass, the mass of it is on the top of the table, let's say mg, mass times gravitational acceleration. So that's the force, this much force it is applied on by the thing on top of the table. In return, the table applies another force, and that is the normal force, which is upward. So these two forces, they are equal in magnitude and opposite in direction. Means the weight of the object is downward towards the earth, and the normal force is upward, which is away from the earth, right? Upward. So these are action and reaction. Now let's specifically talk about these two things. Here in this diagram, what you are seeing, there is a book and there is a crate. Like on the right side, you are seeing a book and the crate. The book is leaning against the crate, right? It is not moving. Nothing is moving. Neither the crate is moving nor the book is moving. Both of them are at rest. Your mic is producing a little bit noise. Just mute yourself. Okay. So both of them are producing applying a force on each other. So the book is applying a force on the crate, and the crate is in return applying a force on the book. So there is a little bit concept about the notation. Let me introduce the notations. And once we get along with these notation and understand them, then I think it will be a lot easier for us. Here in this case, the figure 2, second part of the figure, it shows that the crate, let's say this is the point, it is representing the crate. There is a force on the crate from the block. Just look the notation. Whenever we are writing this force, and we are saying that the force on the crate from the block, this will be the notation for this, on the crate from the block, okay? And if we are saying that the force on the book from the crate, force on the book from the crate. So these are the BC and CB. These are the notation you guys need to understand it, because in future there will be problems, you will be solving them, and most of the time the notation will be given like this. It will be sometimes not even mentioned that which thing is applying the force on what thing. But based on the notation, you should be knowing that this force is coming from this object and it is applied on the other object. So if the notation is like this, FCB, it means that the force applied on the crate from the block. If the notation was this, it will be the force applied on the book from the crate. So these are the notations that you should be understanding them.
Doctor.
Yes.
Is they equal in magnitude?
They are equal in magnitude. Like whenever you are seeing this equation like FBC equal to FCB, there is no vector notation on top of them. So when I'm putting the notation like this, right? I'm putting like this, since because there is no vector sense to it, so therefore the magnitude of this is equal to this, either representing magnitude like this or representing magnitude like this. Both of them are fine ways of representing the magnitudes, okay? But whenever I'm just taking this outside of the modulus and not talking about the magnitude, then I can put this as vector CB equal to negative of vector BC. Okay, so the force on the book from the crate and force on the crate from the block. These are negative sign, and it doesn't matter whether the negative sign is on to the left or to the right, but it just tells you the direction that these two forces are opposite to each other. And if you choose, like let's say you are using the XYZ coordinates and you choose the positive X to be representing the positive forces and the negative X to be representing negative forces, then in that case you can definitely assign the negative sign to a specific side. Okay. Here there is another example of the action and reaction thing. This is another law. we see there is this rocket. The rocket is fired up. It is going up. So the rocket is ejecting a lot of hot air and gases, right? So that gas is coming out. It is rushing out of the crate, the rocket, and as a result, the rocket is pushed upward. So the action part is just when the rocket is ejecting the gases, and reaction part is when the rocket is moving under the action of that force. Okay, so this is the action and reaction, and again you are seeing the notation here, like the force on the air from the rocket, right? And then this is the force on the rocket from the air. The notation is again switched over, like the RA and AR. These are the two different notations, okay? So action and reaction, like if we go and extend with our daily life objects, you are seeing the action and reaction is everywhere. If I'm pushing on this wall, this will be to the left, away from your page. You are seeing it. So the wall is applying another force on me. That's one thing. Second is that if I'm walking on the ground, my foot is pushing the ground to the back side, right? And then as a result, I'm moving forward. So that is the action and reaction again. So a lot of things, whenever we are talking about the action and reaction, it should be understood. Whenever we are applying the force, there is a reaction force to it. But one thing more to be extremely cautious about it, and that is that the action and reaction, it should be from two interacting bodies. Okay, so one interacting body is applying the force on another one, and the next interacting body is applying the force on the first one. It should be in that way. Okay, if it was not like this, if there was a third body and we are bringing the consideration of the third body into it, then the entire discussion will be vague and it will not be considered action and reaction. Let me tell you this. Here, in this example, figure A, you are seeing there is earth. On top of the earth, there is a table. And on the top of the table, there is a cantaloupe. Okay? So what we have been discussing so far, that if you talk about the forces between the table and the cantaloupe, then that will be considered action and reaction. The table is applying the normal force on the cantaloupe, and the cantaloupe is applying its weight downward. That's the weight force. It is applying on the table. So there are two interacting bodies, table and cantaloupe, and these two are applying the forces on each other. But now, if I bring the discussion of the third object, which is the earth in this case, and I'm saying, as you are seeing in this diagram B, that there is a force on the cantaloupe from the table, okay, FCT. That's a one force. And then I'm considering another force, the force on the cantaloupe from the earth. These are the second force. So these are the two forces I'm discussing. The force in the quantity, these are two forces. But if you look at the origin of the two forces, one is the earth, another one is the table. Both of these forces are applied on the cantaloupe. But these are not action and reaction. These are two separate forces. Okay? And this is happening between three bodies, cantaloupe, table, and earth. Okay? But on the other hand, if I remove this table out of the question, like remove this from the equation and bring it here. When you put the cantaloupe without any table, then there will be the force between the cantaloupe and the earth. And whenever I'm discussing the two forces now, which is the earth applying a force on the cantaloupe, and as a result, the cantaloupe is applying another force on the earth. Okay? Now you are seeing two bodies, and then there are two forces. Those two forces are, these two forces are action and reaction. Okay? Because the origin of these two forces are different and they are applied on two different bodies, not a single thing. Okay? One is applied on the earth and another one is applied on the cantaloupe. While in the first case, the two forces which we were discussing, both of them were applied only on the cantaloupe. So that was not considered third law force pair. While in this case, these two forces are considered third law force pairs. This is just the discussion what I just mentioned there, like what is considered a third law force pair and what is not considered third law force pair. So in simple words, whenever you are talking about the two forces, these two forces should be between two interacting bodies, and it should be applied on the two interacting bodies. Like you are standing on the earth, so you are applying your force on the earth is applying another force on you. So there are two things, and the forces are applied also on the two objects. Okay, so that will be considered third law force pair. Any question here? Because we are going towards the application.
So if there is two bodies and they are acting forces in each other, that's an action reaction.
That's action and reaction, yes.
If there is three bodies, is it possible to be like an action reaction? If the three objects, not three bodies, sorry.
Okay. If you consider the figure number 1, figure A, there are three objects: cantaloupe, table, and the earth.
Yeah.
And if you are looking for the action and reaction forces, there will be different origins of that. First of all, the cantaloupe is applying the force on the table, and the table is applying another force on the cantaloupe. That is the third law force pair in action and reaction. But if you are bringing into the question that we are saying the table is applying a force on the cantaloupe, and then we say the earth is applying another force on the cantaloupe, then those are not action and reaction, because the earth is applying different force and the table is applying another force, right?
So
These are the
forces have to act in each other.
What is that?
So both objects have to act in the same object, like
Yes, exactly.
the ball on the table, and the table and the ball.
Exactly. So in that case, the table and the earth, both of them were acting on the single object, and we just said these two forces are applied on the cantaloupe. So that is not action and reaction, but in reality, there we are just saying that these many forces are here acting on cantaloupe. We just discussed the forces on one body. But if we are considering the action and reaction, it should be including two objects, the cantaloupe and the table, or the table and the earth, or the cantaloupe and the earth, right? So then you can just make those kind of things. Let's say in the figure C, which you are seeing, there is a cantaloupe and the earth. So one force is on the cantaloupe and the second force is on the earth. So when you see two objects, the force should be applied on the two objects, and that should be considered action and reaction. But if we are saying these many forces are on the single object, then yes, we are saying there are forces, and which is true, there are forces, but all the forces are only on single object, which is not action and reaction. You got it?
Yeah, I got it. Thank you.
Okay. Any other question, guys? Okay. This is the checkpoint based on the previous slide. Suppose that the cantaloupe and the table in figure 5.11 are in an elevator cab that begins to accelerate upward. So when the elevator is accelerating upward, we know there is definitely a force because there is acceleration now. Now, do the magnitude of FTC and FCT increase, decrease, or stay the same? What is your take on it?
Decrease, because the gravity will be low.
So if the elevator is going upward, and have you all went up and down in elevators. When the elevator goes upward, then you may have been noticing that you feel a little bit heavier at your feet, right? Is this the case?
Yes.
Yes.
Yes. Okay, so then the same thing, like since you had your weight, which was mg, but when the elevator was going upward, there is a fair amount of force applied just because of that inertia, and you feel a little bit heavier on your feet. So remember that the equation which we were discussing, that if there is an elevator, there is a tension in the elevator, this cab, and then there is the mg, which is your weight or the object, anything inside the elevator. When it goes upward, like this, we say T minus mg, because T is to the positive y and g is to the negative y. So T minus mg is equal to ma. And this is the acceleration, which is the cab is going upward, right? So we say that the tension, which is mg plus ma. Okay, that is the when we were discussing the tensions. But since the FCT, if you look at the FCT, it is actually the normal force, which we just said Fn. So this is the normal force. All it will be just replacing is the T by Fn, because now the discussion is just only about the normal force. So Fn, it is increased because mg was the original weight of the cantaloupe, and it is increased by the amount of ma. If it was coming down, then you will be seeing that the acceleration is going to be negative, and therefore the cantaloupe will be felt a little bit lighter than its original weight. Okay. Are those two forces still equal in magnitude and opposite in direction? The FCT and FTC, are these opposite and equal in magnitude?
No.
Okay.
Yes, maybe.
Opposite, not equal magnitude.
They're opposite, certainly opposite, but the trouble point is that whether they are equal or not. And,
No.
and the answer for that is yes, they are equal, because until you see that the cantaloupe is able to break the surface of the earth, the surface of the table, or sink inside this surface of the table, then they are equal. Are the table surface is able to jump the cantaloupe like the spring? Okay. If there was not the situation, then the FCT and FTC both are still equal. Like the more force you are feel when you are going up in the elevator, you are feeling more force at your like your legs, but the elevator surface is providing enough support to you to keep you at the same level. So therefore, your action on the elevator surface and reaction are equal. Yes. Another question is, do the magnitude of the FCE, which is the force on the cantaloupe from the earth, and another one is FEC, which is the force on the earth applied by the cantaloupe, increase, decrease, or stay same?
I think stay the same.
They stay the same because the person weight is the person weight. That is equal to the mass times the gravitational acceleration. It is not the apparent weight. This is what we are discussing. It is also called apparent weight. Your apparent weight can increase or decrease based on the motion. If you are going in the airplane and the airplane was taking a little bit sharp a turn upward or a sharp turn downward, then your weight could be a little bit heavier or lighter than your original weight. And that is called apparent weight. But your true weight is always mg. So therefore, the FCE and FEC, both of them are the same. They still doesn't change because it's the true force applied by the Earth, right? Are those two forces still equal in magnitude and opposite in direction? The answer is yes. Okay. Any question here?
No.
Okay. This is another problem. We are now going into the applications of the Newton's laws. We are applying all Newton laws now in order to solve different problems. So here in this case, you are seeing a block that is on top of the table, and there is another block which is hanging. So the capital M block, it is up there on the table, and the small m block, it is hanging. So a block S of mass m, 3.3 kilogram, is free to move on a horizontal frictionless surface. It is connected by a massless cord that wraps over a frictionless massless pulley to a second block H of mass m, 2.1 kilogram. As the hanging block H falls, the sliding block S accelerates to the right. Find the acceleration of the block S and acceleration of the block H and the tension in the core. Okay, so these are the things which you need to determine here. So before going into the solution, let me describe the situation. You are seeing the figure part A, this one, which I'm pointing my laser on. We are analyzing the forces on the block, and you are seeing the one force is the weight of the block, which is downward. Another one is the reaction force from the table surface, that is the normal force, these are upward. The weight and the normal force, both of them are along y-axis, okay? And they are equal in magnitude in opposite in direction, completely cancel each other. So therefore, we are not bringing this into the discussion, because the block M, it is sliding on the table towards positive x-axis. It doesn't go along y-axis. If it was going, then we will be discussing the Fn and Fg as well, okay? But now, the tension force, this is the only force that is pulling on this block, which is going to the right side. We want to determine how much is the acceleration there, okay, in the block S. So let me solve this problem on the board here. There is this pulley and there is this block. The string is attaching the two blocks. So this is the small m block, okay, lowercase mg is the force that is applying. And we know that when there is this force downward, as a result, there is a tension force in the string which is upward. Now, we also had learned that if there is a pulley, this tension force from the lower block, and here is an equal amount of tension from the upper block, both of them will be pointing towards the pulley, like this, okay? So these are the two tensions. Now we also know that the mass of this block is capital M, that it is provided there. And it is accelerated to the right side by an acceleration A. So we know that by the same amount, this one is accelerated downward, it will be stretched to the right side by the same amount. So the acceleration here is downward and acceleration here is to the right side, because both of these blocks are connected by the single string. So now solve the problems for one part first and then for the second one. So let's do it for this one. Here we see that this is the force tension for the upper block, and that is accelerating the block by amount A. So by Newton's second law, the force tension is equal to MA. This one. Okay? This one, we got it. But since they're asking for the acceleration, but we don't know how much is this acceleration, right? This acceleration, the tension. We don't know the tension and we also don't know the acceleration. Both of them are unknown in this equation. I need another equation to solve this problem. When I'm solving the problem for the hanging mass, how should I do? I need your input.
T equals mg.
No, because it is moving downward, right? How many forces are upward?
One upward, which is T minus mg.
T minus mg.
Okay, T is upward. You guys remember that by the Newton's second law, we said F net is equal to MA. That was the equation we had derived. So the net force, when we are looking for, there are two forces. One is the tension, which is upward, T. I'm taking that positive. Mg is another force, which is downward. I'm taking that negative. And then On right side, we also know that this acceleration is to the negative side. By the same, when I apply the convention, I should be applying the same convention everywhere. Means if I'm considering this minus y plus y, I should be considering this negative sign for all of them in the same ways. So minus mg, and on right side I'm also having minus ma, just because this is also pointing to the negative y-axis. So looking at this equation, this is my second equation, and this is the first equation. I don't have any information about tension, so let's eliminate tension. Let's put for capital MA for this tension. Capital MA minus mg equal to minus MA. This is the equation. Now I got. Since the looking at this equation, we know that the capital M, the value we know it, the small m we also know it, and g is constant. The only unknown is now acceleration. We need to solve this for that. So I'm moving this ma to the right side. So I'll be left with minus mg is equal to minus ma minus capital A. You know that negative sign is everywhere, so just multiply this with -1. Everything will become positive, and take the acceleration common. Take the acceleration common. I will be left with the small m plus capital M equal to small m times g, and then divided both sides by this. Mg divided by m plus capital M. Now, looking at this problem, we know that the mass, small mass, capital mass, and g, all things are known. You guys can determine the A. Any question here?
It's clear.
Okay.
I just want to check the answer, Doctor.
Yes,
Is it going?
3.6 is the acceleration, and if you want to determine tension, then you already got acceleration multiplied with A. Multiply that with the M.
Okay, thank you.
Yeah. Okay, this is another situation. It was not always a luxury that you are pulling things on the straight ground, like horizontal ground. Sometimes you also need to move something uphill. So we are simplifying that situation now and just putting a plane, which is also a frictionless plane. Okay. So a cord pulls on a box of sea biscuits up along a frictionless plane inclined at 30 degrees. So the angle it makes with respect to horizontal axis, it is 30. The box has mass 5 kilograms, and the force from the cord has magnitude 25 Newton. That is the tension force. What is the block's acceleration along the inclined plane? So guys, I'm going to tell you there are the forces. The situation is a little bit different now. So pay attention to it, because the force resolution here is a little bit, that's the first tricky point. If you understood that, the rest of the problem will be extremely simple and straightforward. So this is the angle theta. The block is here. And now it is accelerated along this direction by the cord. So we know that the tension right there with respect to this block will be along the plane. Now, it does not matter wherever the block is, but if this is the earth, then the normal, the weight is going to be straight towards the earth. The weight line, like this, is we just going straight towards earth, no matter where the block is, on which surface it is. Okay? So here we got into a situation. And the situation is this. The tension is here. The mg is here. These are two forces, and both of the forces are neither along x-axis neither along y-axis, okay? So if it is not along x-axis and not along y-axis either, what we need to do is to split the force, one of them, so that we need to make them in the x and y axis. So for this problem specifically, I will consider my xy plane like this. Look at this trick here. So my xy plane will be like this. I'm putting my x-axis just like this. So that my x-axis is going to be parallel to this plus x, and y is going to be like this. Rotated coordinate system that we applied in the chapter 2 or something. So plus x and plus y, this is my coordinate system. Now, you also notice that if this block is supported by this plane, then there is a force from the plane. And that force is a normal plane, a normal force, and it is just away from the surface, like this. So Fn is going to be upward. Okay? Since I need, for this normal force, if it was only normal force, then this block will be flying away from the surface, because the normal force will be more, but it is balanced by something else. And there's some other forces here. What I need to do, just pull a straight line, right? Sketch a straight line, just opposite to the normal force. So it is this line. And now I also see that there is this tension force, but when you are pulling something on top of the plane, it is a little bit harder to pull it as compared to pulling it on the horizontal plane. So there is something going on. What is that something? And that something is here. If I have this mg, the tension this way, I need another force just parallel to that, but opposite direction, like this, okay? Like this.
Okay.
If you look at this, this is your right angle triangle. This is 90 degree. This theta and this theta are going to be the same. By trigonometric identities, or you are also applying the geometric functions. So this angle and this angle are same. This was 30, then this is also going to be 30. If this was the hypotenuse, mg is the hypotenuse, this mg, right? We know this is the x-axis of that, right? Like the base. So it is going to be mg cosine theta. And this is the perpendicular of that triangle. It is going to be mg sine theta. Okay. Once that is done, I need to analyze the forces. And the forces, what I need to analyze for the acceleration, because the acceleration is happening along the plane. So let's resolve the forces along this x-axis. When we are resolving the forces, we know this tension is to the positive x-axis. So if we are taking that positive, the opposite force is here, mg sine theta, which is here. It is pointing to the negative x-axis. So minus mg sine theta. And under the influence of this force and this force, the black is going upward. So if the black is going upward, I will be putting the acceleration positive just because it is pointing to the positive x-axis. So I'll be putting mass of the black times the acceleration of that. Okay? Now, all I need to do is to determine the acceleration. I will be looking at the equation. If I know the tension, which is already known, shown in the problem, mass of the black is also shown in the problem. G is constant, theta is given to me, and this is again mass of the black. So everything is known. This one equation is working the job for us, so we just divide both sides by mass. So therefore, acceleration is going to be t minus mg sine theta divided by m. And we can put the values from the equation, which here is going to be 25 minus 5 kilogram times 9.8 times sine 30 divided by, again, mass, which is 5 kilogram. It will give us the acceleration. Any question here?
Why we put sine theta?
Why did we put sine theta? Because we wanted to split this mg force in two coordinates. One is the component mg cosine theta, one is m sine theta, mg sine theta. So we need to resolve the forces along x-axis and along y-axis, okay? Because if I'm just attempting this problem without splitting this in components, then it will be extremely difficult problem. Because the mg, whatever it is, I don't know it otherwise. So I need to know it from this, and also exactly know how much the force is applied opposite the retention and opposite to the normal force.
Doctor,
Yeah, any other question?
if I want to put the theta with the x-axis because I feel it is better for me, what should I
You
do
want to put the theta into x-axis?
for the weight mg?
Theta is right here. Where do you want to put it?
I want to make it with respect to x-axis.
This one here?
No, with respect to the x-axis.
So this is your x-axis. This is your tilted coordinates, right? X and y.
Yeah.
Yeah.
So
I think he don't want to rotate the x and y axis.
Okay. If you don't want to rotate it, there will be another big problem for you.
It will be difficult, right?
It will be more difficult, and the difficulty is coming from the two aspects. First of all, you need to sketch the angle of the tension force with respect to x-axis. So which is known, which is 30 degrees. Same angle here, okay? And now you need to have the two components of the tension, which is the x and y. So the t sine theta will be upward and t cosine theta will be to the right. That's one thing. But here you see this is the t sine theta, and this is t cosine theta. And if you look at these two forces, neither of them is along the plane. But at the end, you need acceleration along the plane because the plug is going straight across the plane, like along the plane. So if you go with this, at the end, you will be able to reach out to your answer, but that will be extremely lengthy problem. The way in which we are resolving this and using the tilted coordinates, it is simplifying everything for us.
Okay.
Yeah. There is another problem here. Just read the statement, guys. Okay, reading a force from a graph. This figure, which is figure A here, in this there are two forces applied to a 4-kilogram block on a frictionless floor, but only force F1 is indicated. That force has a fixed magnitude and can be applied at any adjustable angle to the positive axis of the x-axis. So F1 is flexible. You can move up and down along the directions. But the F2 is horizontal and fixed in both in magnitude and angle. So it is applied only in positive x-axis, okay? It's just say horizontal, so it could be positive and negative. And also both fixed in magnitude and angle. Figure B gives the horizontal acceleration AX of the block for any given value of theta from 0 to 90 degrees. What is the value of AX for theta 180? So it is asking a lot of questions, and since we are attempting to determine what is that unknown force, okay? So we need to begin the problem by attempting it and a little bit supposing the problem, like how it is going to be. So here we need to apply the force F1, and also we need to see how much is the acceleration there. Okay, and at the end, once we determine the second force, then the next question is asked, what will be the AX when the theta is 180, which is not shown in the graph. So we know this this problem can be like this. Let's say this is your block, and here F1 is applied, and if F1 is making an angle theta. But also, we know that there is a force, and suppose that force for now, at least they say it is horizontal, and it has fixed magnitude and angle. So just suppose it like this. If it is to the positive x-axis, at the end, if we determine that the F2 is negative, then it would be means that it is pointing into the negative x-axis rather than the positive, opposite to what we suppose. Okay. Now, once these two forces are applied, we also know that they will be sketching the pulling this block in the x-axis. So the acceleration component AX is going to be this direction, horizontal. So let's resolve the forces horizontally. Therefore, we also need to resolve this force F1 horizontally as well. So one force component is Fx, and here Fy, F1y and F1x. We know that F1y doesn't do any job for us because it is just pointing upward and the block is not going in that direction either. So we just need to consider the forces along x-axis. So one is F1x plus F2y equal to, this is the total force applied on the block, and they are moving the block along the x-axis, so AX. F1x, we also know it, that is going to be F1 cosine theta. So F1 cosine theta plus F2 equal to M AX. This is our equation 1. Now we need to work with the graph. From the graph, when the angle is 0, just take the extreme cases. When the angle is 0, at that the acceleration is 3 meters per second square. So angle 0, cosine 0 is 1, right? Cosine 0
Is 1.
1. So F1 plus F2, we got it to be mass times the acceleration, and this is 3, and the mass is 4. So in total, we are getting it to be 12. 4 times 3, it is 12 Newton. Okay. Now, we consider the second case, and in that case, we are taking the angle equal to 90. So when the angle is 90, at that the acceleration AX is 0.5. So what we will be doing, we are putting the cosine 90 is 0, so therefore we left with only F2 force. And right side, this is the mass is 4 and the acceleration is 0.5. So it is giving us 2 Newton. In the statement of the problem, they said that the F2 is fixed in magnitude as well as in angle. So we just take the magnitude now, and we proceed to equation 2 to determine F1. All we need to do is to put the value of F2 in equation 2, which will give us the F1 equal to 12 minus 2 equal to 10. So F1 is going to be 10 Newton, while F2 is 2 Newton. Once these are known, at the end they're asking determine the AX for which the angle is 180. Can you guys determine that?
10 minus 2.
Negative 2.
Negative 2.
It will be, since there's a
minus 10.
this is not going to be minus 2. Just pay attention to it. Where is the theta? With the F1 or F2?
F1.
The F1.
F1. So what will be the negative sign then? Negative
F1 cosine.
Yeah, like this. Okay, let me clean this.
Okay.
It will be 10 cosine 180 plus 2 Newton equal to 4 times AX. So you see the negative sign, instead of negative 2, it is here. So it is going to be negative 10.
Yes.
Okay, negative 10 plus 2 is minus 8, and divide by 4, it is going to give us the AX equal to minus 2 meters per second square. So there's going to be the answer. Any question here?
Dr. White's minus 10 because the cosine is 180, right?
Cosine 180, yes.
Okay. Again, thank you.
Yeah. Okay. This is another problem, guys. And here we will. Did you guys record your attendance?
Oh, for the first time, yeah.
Yes.
Okay.
Yes, I recorded.
Oh, I
Yes.
didn't.
In the beginning.
Okay. If you have recorded it, it's fine. I will be continuing with this problem at when the class time overs. You can leave, but the students who stay with me, they will be able to see the end of this problem.
Sir, I have a question quickly.
Yeah.
For the Willy plus time zone, you want it in Riyadh time zone, correct?
Yes. Yeah.
Okay, thank you. That's it. Have a good day. See you next week.
Yeah. And also I'm thinking to take a quiz in chapter 4. A quiz in chapter 4 on Sunday. Okay. So Sunday we will have a quiz in chapter 4.
Doctor, can you make it Monday or Thursday because we have
We have a math exam.
Yes.
Yeah.
Major.
It's major.
Okay. How about Monday?
Tuesday better.
It's okay.
Okay.
If you don't have any problem.
Tuesday, it's okay.
Tuesday.
Okay, thank you.
Yeah.
Thank you.
Chapter 4. Okay. Which is already prepared for you guys. I think you already did a good job in that.
Yeah.
Okay.